Hello friends, welcome to engineering tutorial. So we'll extend our discussion on sensors, transducers and instrumentation, and we'll extend our discussion on level measurement. Previously we discussed about level measurement using piezoelectric, magnetostrictive and strain gauge sensor. In this video we are going to discuss the same with LVDT. We have discussed about LVDT. So first we'll just in a quick manner we'll discuss the basics of LVDT, and then we'll discuss how we can utilize that to measure liquid level in a container. Now LVDT, which is the short form for linear variable displacement transformer. Okay, so it is a secondary transducer. Okay, we are all familiar with the definition of primary and secondary transducers. Primary transducers convert physical parameter at the input side into some kind of mechanical movement at the output side, linear or rotational movement. Secondary transducers, they convert the physical parameter into some kind of electrical signal, voltage or current. As everything is electrical and electronic in nature these days, it is better to convert it into a voltage or current signal so that we can use appropriate signal conditioning circuitry and analog to digital conversion methods to directly display it in the form of a digital output. So it can be used for various parameter measurement, displacement, force, pressure, acceleration. So we will utilize that principle to measure liquid level. So the basic design of an LVDT is this. First we have a hollow bobbin, okay, this, and then we have a primary winding and two secondary windings which are in phase opposition with respect to each other. Okay, then we have a ferromagnetic core which is inserted inside this hollow bobbin, and this is free to move. This portion, this portion and this portion, it is free to move. Actually this movable ferromagnetic core is connected to the source of displacement, force, pressure, movement, whatever it is connected to that source. So now we have a AC supply which is connected across the primary winding. So what happens when this hollow bobbin, this portion, this end is in between here, in this position, exactly in between these two secondary windings, the degree of coupling of the primary winding with each of these secondary windings, it is the same. Okay, coefficient of coupling, okay, that it is the same. When it moves from this center position, which is called as null position, either to the left or to the right, okay, this is the position where it is initially it is present. Okay, this hollow bobbin, this end, this right end, it is present in this position, that is the null position. In that case the degree of coupling with each of these secondary windings, it is the same. So the net output, which is one secondary winding minus the other secondary winding, that is equal to 0 volt. Why? Because as the degree of coupling with each of these secondary windings is the same, so each of these secondary windings will have the same voltage output. Okay, equal in magnitude but opposite in direction. That's why the net output voltage, that is equal to 0 volt. Now when this bobbin, it moves either to the left or to the right, okay, the degree of coupling with one of the secondary windings, it increases than the other. Okay, it no longer stays the same. One primary winding with one secondary winding, the degree of coupling, it increases, and with the other secondary winding, the degree of coupling, it decreases. So the secondary winding with which the degree of coupling increases, that will generate a greater secondary winding potential. Let us say the degree of coupling with the first secondary winding, it increases, so the voltage across that secondary winding will be greater than the other. In that case, it will produce a non-zero output, net output it will be non-zero. And when ES2 will be greater than ES1, that is the second secondary winding output will be greater than the first secondary winding output, it will be equal in magnitude but opposite in sign, because ES1 comes first, then ES2. Okay, so magnitude throughout the transition from one way to another, the magnitude will keep, it will be the same, but only the sign will be opposite. So that way it will work. Okay, so this is the null position which I was talking about, exactly in the center, the null position. In this case, both secondary winding potentials, they are equal and the net output is 0. In this case, it moves to the right, so it will produce a non-zero output depending upon the degree of coupling. And likewise, when it will go to this end, again it will produce a non-zero output but with the opposite sign. Okay, like this. Now, the mathematical representation of the output voltage, it is given in this way. It is a complicated expression. If you want to just have a look at it, just have a look at it and write it down somewhere. There is no need to remember anything, but just for the sake of your understanding, I am putting this mathematical relationship where the output voltage is given by this expression. Very complicated, lengthy expression. It is given by 16 pi q f I p, means I subscript p, n subscript p, n subscript s divided by 10 to the power 9 log to the base e, r subscript o by r subscript I into 2bx by 3w into 1 minus x square by 2b square. Very complicated and lengthy expression. These are the parameters where f is the excitation frequency of the AC supply which is connected. Everything with the subscript P related to the primary winding, where IP is the primary current, NP is the number of turns in the primary winding, NS is the number of turns in the secondary winding, B is the width of the primary coil, W is the width of the secondary coil, X is the core displacement, that is displacement of the core from the null position, center position on either side, R0 is the outer radius of the coil, Ri is the inner radius of the coil. So this is the whole expression of, the whole operating principle of LVDT. Now how we can use it to measure level? Now I think we discussed one thing, level measurement using LVDT, which was like this, where we connect the rod, that is the ferromagnetic core, with the rod of the float, okay, the connecting rod, and when the liquid level increases or decreases, this LVDT, it will change its position from the null position and will give us a particular output. But this principle, this technique, it has its advantages, but the major disadvantage is that the level measurement is only limited to the range from here to here. The rod is in this position, it can only go upwards up to this point, the extreme end of the LVDT at the topmost side, and here, the bottommost end of the LVDT. Only this much, only in this range the level can be detected. Okay, that is the major disadvantage, but it is sometimes used in some cases, but in majority of cases you will find arrangements like this. First, a single LVDT sensor in both ends, it is connected, okay, where the ferromagnetic core is insulated and exposed to the float and rod arrangement. So when the liquid level, it goes up and down, the rod, it strikes the movable ferromagnetic core. Like I said, it strikes the movable ferromagnetic core, and as a result of that, the ferromagnetic core, it gets disturbed from its null position, from its center position, and it produces a non-zero voltage output. This is a single sensor arrangement where we don't want the liquid level either to go above a certain level or below a certain level. So we want to generate an alarm. So this is the single LVDT sensor arrangement. We can also have continuous level tracking, as we have done with other sensors, where we connect multiple sensors. So multiple LVDT sensors, depending upon the length of the container, 5, 10, 15, whatever number of sensors we want to connect, how many number of measurements we want, depending on that we can connect as many sensors. So the same principle, as the liquid level changes in the container, the float and rod arrangement, it goes up and down, and as the rod strikes the core, okay, of the LVDT sensors, it undergoes movement from its equilibrium center or null position, and it produces a non-zero electrical output. So this is the basic operating principle of liquid level measurement using LVDT. Okay, so this is the thing. So let us try to understand the working of LVDT level measurement technique using a three-dimensional perspective. So this is the basic LVDT arrangement. So we have the ferromagnetic core here, okay. So this is the movable portion. So when it moves away from the equilibrium position to one end and then to the other, the degree of coupling of the primary winding with each of these secondary windings, it changes, and as a result of that, it produces a non-zero differential output voltage. So this ferromagnetic core is connected to the source of displacement or the physical parameter which is to be measured. In this case, it is connected to the float which is placed on the surface of the liquid. So first we have the LVDT sensors, which can be connected in a single sensor arrangement or a multiple sensor arrangement. It is connected across the walls, side walls of the liquid container, and when the liquid level it changes, the float which is floating on the surface of the liquid, it moves up and down, and the rod, it strikes the ferromagnetic core of the LVDT sensor, and when it strikes, that particular sensor is triggered, or that pair of sensor is triggered, and gives us information about the the liquid level which is at a particular height. Okay, so this is the thing, okay, like this, along with the level. And here, in case of multiple sensor arrangement also, there is more continuous tracking, where when the liquid level it goes up and down, when it strikes the ferromagnetic core of the LVDT sensors, the multiple LVDT sensors, these sensors are triggered depending upon the position of the float and rod. Okay, so this is all about liquid level measurement using LVDT. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.